This is Physics 104A at Porterville College, homework chapter 12 on static equilibrium, starting with number 14. I've drawn a picture of the object. The blue outline is just showing an arbitrary shape. And I've drawn the object on a Cartesian coordinate plane. You can see the force vectors I've drawn at the right angles and right proportions being applied to these specific points. And the question says to show for part A that the sum of the forces is equal to 0, and for part B that the net torque about the origin is 0. So for part A, the sum of the forces, we have force 1, which is 2i plus 2j, and I've done it in my vector notation, 2i plus 2j newtons, plus force 2, negative 2 minus 3, or negative 2i hat minus 3j hat newtons, and force 3 plus 0 in the I hat direction and 1 in the j hat direction, so that's this one right here. And you can see the x's, 2, negative 2, and 0 add up to 0. The y's, 2, negative 3, and 1, they add up to 0. So we have a 0, 0 vector. Part B. Show that the torque about the origin is 0. So we're going to add up the three torques. Torque on 1, or torque from force 1 plus torque from force 2 plus torque from force 3. And each torque is the cross vector product of R and F. Now R is the vector from the origin. In this case, since we're looking at the pivot being the origin, we can just do the coordinate of the placement of the force. In the next problem, number 15, it's going to change that on us, but for now we can just use the different points. So remember how we do a cross product, I hat, j hat, k hat. For force 1, it's being applied to point 2, 0, so x is 2, y is 0, and z is 0. And here's the force, 2, 2, 0. And we'll take the determinant of that matrix. For the second force, it's being applied at negative 1, 0. And so there's negative 1, 0, 0. Everything in the z direction, the k hat direction, the forces and the positions is just going to be 0 throughout this problem. And there's the force. Take the determinant of that matrix. And then for the third one, where the r vector is negative 7, 1, 0. Taking the determinants of these matrices, I'll just go through the first one. We do I hat, and then the determinant of this 2 by 2 matrix, which is 0 times 0 minus 0 times 2, so that's 0, minus j hat, and it's the determinant of the 2 by 2 matrix that doesn't include the j hat column, so 2 times 0 minus 0 times 2, and that goes to 0. Plus k hat times, and it's the determinant of this matrix, 2 times 2, which is 4, minus 0 times 2. So the determinant of this entire matrix is 4k hat. For the second one, it's 3k hat. For the third one, it's negative 7k hat. And those vectors add up to be 0. Number 15. Is the same object, but what we're showing here is that the choice of pivot point doesn't matter. So we're going to do the same as we did in 14, but the pivot point is going to be, instead of the origin, it's going to be 3, 2. So here's the pivot point. Now when we do our r vectors, we have to do it from the pivot point to where the force is being applied. So this is where a picture really helps. And you can see the r vector from this pivot point at 3, 2 down to where the force is applied. I just drew a picture so we can count the squares. And we can see it's -1 in the x direction and -2 in the y direction. So -1, -2. R2, to get from this pivot to the point where 2 is, force 2 is applied, we can see it goes to the left 1, 2, 3, 4. So that's an x of -4 and down 2. 1, 2. -4, -2. The third vector, I didn't draw it to avoid clutter, but the third vector goes from here to F3. So that's over to the left 10 and down 1. So there's -10, -1. Once you get that worked out, the rest of the problem is the same as we did in number 14. So we just once again do the sum of the torques, set up our matrices to do the determinants, but the only thing different now in this part from number 14 is we have new r vectors. So here -1, -2, 0, -4, -2, 0, and -10, -1, 0. Take the determinants of these matrices. Sorry about the mess here. This first one is -2 minus -4. So we get 2k hat plus 8k hat minus 10k hat. And that's a 0 vector. B doesn't do anything, there's no added skills here, just more practice of doing the same thing. For B, the pivot is -7, 1. It's actually going to be slightly easier than part A because one of the torques is just going to be 0. So here's our pivot point, and R1 is then from the pivot point to where force 1 is being applied, which is 9 to the right and 1 down. So, excuse me. Okay, sorry about that. 9, -1. R2 is, let's see, 6 to the right and 1 down. And R3 is 0, 0, because that's where it is. So we know right away the torque of F3 around that pivot point is 0, because it's being applied right at the pivot point. But in case we don't see that, that'll come out in the math. So here's our new vectors. We have the r's of 9, -1, 0, 6, -1, 0, and here's 0, 0, 0. These come out to be 20k hat for the first one, plus -20k hat for the second one, and 0 for the third one, so it comes out to be the 0 vector. Number 17. A thin uniform square plate, that means, the uniform means the density, the mass is distributed evenly throughout. Mass M inside L. Find the magnitude of the gravitational torque on the plate about each of the 3 points shown. Okay, so for part A, I just want you to imagine that this is a square, imagine like on a cork board, and we put a thumbtack right here through A, and it's free to turn. Now you can imagine this square is going to rotate around like this in the clockwise direction. Well, the thing that's going to make it rotate is that gravity pulls it down, and specifically gravity, the force of gravity, is working at the center of the square, at the center of gravity. So we want to see what is that torque. I'm going to show this 2 different ways. One is using the scalar way think of it as the chapter 11 way before we learn to treat torque as a vector. And then I'll do it the chapter 12 way as a vector. So the scalar way is to say torque of A is RF sine theta. Remember that back from chapter 11. That's actually the magnitude of the torque. This is torque about A. So first, the force is mg, the force of gravity. It's acting at a distance of r from the pivot point. Now what is r? We use a little bit of geometry to find that you can think if the diagonal of the square, if the square has a length of L, a diagonal is L times square root of 2. And if you don't believe that, just use Pythagorean theorem, L squared plus L squared, take the square root of that. But it's L times the square root of 2. And this is only half of the diagonal of the square. So it's square root of 2 over 2 times L. So square root of 2 over 2 times L times mg times, that's a 45-degree angle. Sine of 45 is square root of 2 over 2. And that simplifies to 1/2 LmG. Now the vector is into the page, and I get that from, if you use the right-hand rule. Remember, for right-hand rule, you put the vectors tail to tail, R, and the force, and then curl your right hand, curl your fingers in the direction from R to mg, and your thumb will point into the page. And that's the negative z direction, or the negative k hat direction. Now the same problem, but using vectors. Torque is, we set up our matrix, I hat, j hat, k hat. Okay, let me go back up to the picture here. If we take the origin to be A, so that's 0, 0, where is the force being applied? Well, it's being applied up here at, in the x direction, half of L, in the y direction, half of L. And it's not coming out of the page. So that's why I have L over 2 and L over 2 and 0. What is the force? Well, the force is being applied straight in the negative y direction. So 0, negative mg, 0. Take the determinant of that matrix, and you get negative mg L over 2, which is the same as we got using the scalar method, but k hat, oh, and that's a negative sign in the k hat direction. Part B has the pivot being at point B. You can imagine once again on a vertical corkboard sticking a thumbtack in here, and which way will the square rotate, and you can see it's not going to rotate, it's just going to hang there, and so that means it's in static equilibrium. Well, and that tells us that the sum of the torque should be 0. But let's do it the chapter 11 way, then the chapter 12 way. So the torque about B is RF sine theta. Doesn't matter what R is, although it's L over 2. Doesn't matter what F is, although that's mg. The key here is the sine. They're acting at a 180-degree angle to each other. So it makes, or you can say 0-degree angle. Either way, it comes out to be torque is 0. The solution using vectors, I hat, j hat, k hat, 0. Everything is in the j hat direction. So negative L over 2 is where it's being applied, and the force is still negative mg, just like in the previous problem. And when you take the determinant of that matrix, you should get 0. Part C has it pivoting about point C. The two different methods, the scalar method, r times f times sine theta. Here r is half of the side of the square, so L over 2, times the force is mg, times the sine, that's a 90-degree angle in here, and so 1/2 LmG. It's out of the page. You can see that by, if you line up R and mg from tail to tail, your fingers of your right hand curl and your thumb comes out of the page. Treating it as vectors, I hat, j hat, k hat. In this case, the force is being applied from the pivot point at negative L over 2, 0, 0. The force, just like all through parts A and B, 0, negative mg, and 0, and we get a vector of 1/2 lmg k hat. Number 20. I want you to look at my picture and notice there is something that I've left off of this picture. For a reason. 60 kilogram uniform board supported by a pivot 80 centimeters from the left end and by a scale at the right end. I have not drawn the scale. Why not? How far from the left end should a 40 kilogram child sit for the scale to read 0? Okay, so I've drawn all the forces that are applied to the board. We have the child sitting here. I'll make his mass little m, 40 kilograms. The the mass of the entire board, which is acting at its center, and I'll call that capital M. We've got the normal force from the fulcrum right there, which is acting at the pivot point. Those are all the forces. Now there is a scale here, but we're looking for, if this were actually resting on the scale would have a normal force, and that normal force would be what the scale reads. But we're looking for it to be tipping just so there is no normal force, meaning the scale is reading 0. So it's as if the scale weren't there. We should, if the scale is truly reading 0, we should be able to kick that scale away and everything should be in perfect balance. So if you're wondering, why did the author even bother to have a scale? Well, problem number 21, which I didn't assign, involves the reading of the scale. But we'll just stick to what if the scale isn't there. For this to be in equilibrium, the torque about the fulcrum has to be equal to 0. And what are the torques? I do this in the chapter 11 kind of way, just treating them as the scalars, where in the counterclockwise direction that's positive, so yeah, that's positive, and negative in the clockwise direction. I want you to look up here because we need, at the picture, we need to know what the lever arms are. Here's how I've set it up. I've set the distance from the pivot to be the lever arm. So the question is asking where the child should sit, so I've set that up as my X. The center of mass of the board, I put that as 0.4 meters from the fulcrum just because the fulcrum is at 0.8 meters from the left end. So it's 0.8 meters from here to here. If the board is 2.4 meters long, the center of the board is at 1.2. So if to here is 0.8 and to here is 1.2, then there's a 0.4 meter difference or distance between the fulcrum and where the center of mass is. So let's apply those lever arms to right here. We have the torque of the child is little mgx minus the torque of the mass of the board, big mg times 0.4 meters. I've written this in burgundy to show you might guess that the fulcrum itself isn't adding any torque because it's operating at the pivot. But just to show that the math works it out, it's whatever that normal force is times its lever arm of 0, and it just becomes 0 equals 0. Take this equation, first of all, G divides out, and we can solve for X. X equals the ratio of the masses between the board and the child times 0.4. meters, and x equals 0.60 meters. So the child needs to sit 0.60 meters, or 60 centimeters, from the fulcrum, which is 20 centimeters from the left end. Number 24, a portion of a roller coaster track is described by that function, height as a function of x. Find a point where the car could be in static equilibrium. I graphed this on my graphing calculator. I'm going to put my calculator here. Hopefully it stays in focus. Okay, I don't know how well focused that is, but I've typed in the function, so 0.94x minus 0.01x squared. You have to play around with the window. I just messed that up, didn't I? Let's try that again. Hey, let me just type it in again. 0.94x minus 0.01x squared. Okay. You have to play around with the window a bit. I've used a window, x going from -50 to 100, y going from -50 to 50, and that just comes from just playing around with it. And then I hit graph, and I can look at the shape of this roller coaster. This is just the relevant portion. You know, since it's a quadratic equation, it's an upside down parabola, so this is the only curve right there. Where that curve is, that's going to be the point of static equilibrium. And you can set the scale and you can see and guess about where it should be. But you don't need to do that in the graphing calculator. It's just nice to have that ability to be able to predict about what your answer is going to give. Let's do the math now. For the condition for equilibrium is that the derivative is equal to 0. Now, it's actually not just the derivative of the function that's given, particularly it's the derivative of the potential energy function. Notice that what's given is the height function, but you know that height is directly proportional to u, meaning, just write this over here, u is equal to mgh. So really, to find the potential energy function, it's this function here times mg and times mg. But when you're going to take the derivative of it, that mg is going to go away. So really you can get away with, you can include the mg if you want to, but you can get away with just taking the derivative of this function because it's linear, they're linearly related. So we're looking for the derivative of this function, the height function, is equal to 0. So we set that derivative, that's 0.94 minus 0.02x, set it equal to 0, and you get x is 47 meters at a height of 22.1 meters. The height of 22.1 came from taking the 47 meters, plugging it into the height equation. And the nice thing about having done this on the graphing calculator is the graphing calculator showed that it would be at about 50 meters for x. The other part of 24, part B, says, is this equilibrium stable or unstable? Well, to answer that question, first of all, the graphing calculator showed us it's at the maximum and so we can just say based on the graph that it's unstable. But doing the calculus, it's about what the second derivative is. Second derivative, when you do that, is equal to 0.02, and since that's less than 0, that tells us it's a maximum, and that tells us that it's unstable equilibrium. Number 25 is the same concept as number 24, but a bit more advanced. So we have this potential energy curve that's given to us. It's a third order equation. To find the points of equilibrium, and since it's a third order equation, we should expect 2 points of equilibrium, 2 either maxima or minima. Du dx, we take that derivative, it's 6x squared minus 4x minus 7, set it equal to 0. I did the quadratic formula here. You can see how I've worked it out. It came out to 4 plus or minus the square root of 184, divided by 12. And I worked that out to be 2 places. The first is negative 0.797 meters, and the second is 1.464 meters. So those are the 2 places of equilibrium. Now we want to know, are they stable or unstable? So we take the second derivative. The second derivative of the potential energy function is 12x minus 4. So now we plug in our various x values, and when we plug in x being negative 0.797 into this, we get it being negative, it's less than 0, which means it's unstable. For 1.464 being x, we plug that in here, the second derivative, and we get that it's greater than 0. So that means that it's stable. And that's the end of the Chapter 12 homework.